Hello and welcome back. Today we'll be getting into section 2.4 on exact equations. So the basic format that you're going to be looking for equations that are potentially exact, we have some function in terms of one or more variables times dx plus another function, also possibly two variables multiplied by dy and equal to 0. So basically, you might recognize this as doing a partial derivative of a two-variable function. So this is an exact if the partial derivative of m with respect to y is the same as the partial derivative of n with respect to x. Now the reason that works out that way is that this m of xy is the partial derivative with respect to x already. So we basically have partial of function f with respect to x is our m, and partial of f with respect to y is our n. So if we're taking the derivative of a derivative, this is a second derivative. So it's basically derivative of x and y, derivative of y and x. They should give the same result if they are an exact equation. And this is in some region R. So we may have to put some restrictions on x or y depending on if we have, for example, a natural log involved, things like that. If it is exact, we have sort of a multi-step strategy. It'll seem a little much at first. Once you do maybe 2 or 3 problems, you'll start to get the rhythm of it. If it's exact, then there exists an f of x, y, such that, as we said over here, partial derivative of function f with respect to x is our m of x, y, and partial of this function f with respect to y is our n of x, y. And basically, what we can do is then we use this to integrate. I typically just pick the first one. If the first one is super messy, you can, of course, do the second one. So we integrate this partial derivative of f with respect to x. We integrate with respect to x. So then that gives us f of xy. It does let us know what's happening with the stuff in terms of x. I'll just say this is just some arbitrary function relating to the x's, but it won't catch anything that was written just in terms of our y's. So plus some function of y. And the idea is then that we take the derivative again, this time with respect to y. So we differentiate this part, get its derivative, plus g prime of y, and then we remember that n of x is also equal to partial of f with respect to y, set it equal to n of xy. Then we just isolate g prime of y and integrate. And then we're ready for our solution. So then we'll have f of xy is equal to our big final answer, which is equal to some constant. The reason that we're saying they're equal to some constant, if we integrate the right-hand side of this, if our derivative was 0, that means that we had a constant. So any constant has 0 as its derivative. All right, so as I said, it's a little bit much to take in at first glance, but once you've walked through a couple of these, you start to get the hang of it. You get a little bit more used to working with these, and they're not quite as scary as they look at first glance. All right, so first one we'll run through together. 3x squared plus 2y squared times dx plus 4xy plus 6y squared times dy is worth 0. So first I want to check if it's exact. So I'll take the partial of m with respect to y. So I'm sort of switching up the variables. So this derivative was taken with respect to x. Now I'll take that derivative with respect to y. So that drops our 3x squared off of there entirely. So we have 4y. Then I see the partial derivative of n. N was a derivative itself with respect to y, so we'll switch it over to x. So that way our second derivatives each have an x and a y. So this time x is our variable, which makes 4y treated as if it's a constant. The 6y squared drops off. All right, so these two are indeed equal to one another. Therefore, we know that there exists some function xy such that partial of this function f with respect to x gives us the m of x, the 3x squared plus 2y squared. And partial of this mystery function f that we're looking for with respect to y is the n of x, 4xy plus 6y squared. So then we go about trying to find what f looks like. It's important for me to write the x's to look like x's when we're using both variables. My apologies. 3x squared plus 2y squared on there. So I will integrate both sides of this with respect to x. So that will give me at least part of this f of xy. So integral of x squared is x cubed, and it looks like we already have the 3 there we would expect if we differentiated. Since we're treating x as the variable, 2y squared is treated as if it were a constant, which means it had an x attached as well. Again, I'll try to make sure I draw those tails long enough so you can tell the x's and y's apart. Since I integrated just with respect to x, though, I don't know what's happening with g of y entirely yet. So this is at least part of function f. So then I can differentiate this, even though we don't know all the details about it yet, with respect to the variable y. X cubed gets treated as a constant, it will drop off. The middle term there, I'd hang on to the 2. X gets treated as a constant. I'll hang on to the x as well. And derivative of 2y is, or excuse me, derivative of y squared is 2y. So 4xy. Derivative of g of y is whatever g prime of y is. We don't know what g of y is at the moment. So if the partial of f with respect to y is worth this, and the partial of f with respect to y is that, they have to be equal to one another. So that's my next order of business, is just say, okay, 4xy plus g prime of y has to equal 4xy plus 6y squared. The 4xy's will drop, so then g prime of y is 6y squared. So I'll integrate this on both sides. So g of y is worth y squared turns into y cubed. To get a 6 there, I need a 2 here. 3 by 2, 6. Y cubed turns into y squared. And we'll choose c to be 0 at the moment, since we're going to, at the end of the problem, set it equal to arbitrary constant c. So instead of doing a bunch of little plus c's along the way, we do just one to cover all our bases at the end. So now we know what g of y looks like. So now I can take my previous function and tack on the g of y, and then we know that the other side, antiderivative of 0, is c, a constant. So now I can say that f of xy is the x cubed that I had before, plus 2xy squared, or 2y squared x, doesn't matter the order, plus g of y, so plus 2y cubed, and the antiderivative of 0 is c. I believe your author only shows about that much in the final answer. He typically doesn't label the f of xy at the end. I typically would do that. So this is one you can you can check on your own if you differentiate this function with respect to x, do a partial derivative. You get your 3x squared, you get your 2y squared, and multiply by dx. If you differentiate the same function, treating y as the variable and x as if it were a constant, you get your 2x by 2y, which is your 4xy, and derivative of 2y cubed is 6y squared, and you multiply that by dy, and derivative of a constant is a 0. So it does check out based on what you know about taking partial derivatives of functions. All right, these are a little bit longer, so I'll try to keep it all on one page. So we'll just call that good, and I'll use that scratch paper later. Okay, so the next one we're going to have a particular solution. So we'll have e to the x times sine of y plus tangent of y times dx plus e to the x cosine y plus x secant squared y times dy is equal to 0. So first order of business, after you catch your breath from writing all that stuff down, check to see if it's exact. So we'll do the partial derivative of m. M is a derivative itself with respect to x, so we'll flip it over to y to make sure our second derivatives match. So e to the x is treated then as if it were a constant, so he's just along for the ride, and derivative of sine y is cosine y. Derivative of tangent y is secant squared y. So next up I want to take I'll just do under here a little bit just because I write a little bit on the bigger side. Partial of n, treating x as if it were the variable. Again, the reason being n is already a derivative with respect to y, so then we take a second derivative with respect to x and see if it matches when we took the derivatives in the other order. Okay, so now cosine y is treated as if it's a constant, and derivative of e to the x is still e to the x. So far, so good. Again, x is treated as if it's a variable, so secant squared y is a constant. Just bring it along, and derivative of x is 1. And sure enough, that is the same as e to the x cosine y plus secant squared y. So since they are equal to one another, then we know there exists some function f of xy such that partial derivative of this function f with respect to x gave us the m of x, the e to the x sine y plus tangent of y. And partial derivative of this function f, this time treating y as a variable, is what gave us the e to the x cosine y plus x secant squared y. So once we have those in hand, pick one of them and integrate. Again, typically I just grab the first guy and integrate. If we're doing this one, we integrate with respect to x. So then f of xy, sine of y is basically a constant. Antiderivative of e to the x is e to the x. Antiderivative of what's being treated as a constant, because we're integrating with respect to x, would be a first power, so plus x tangent of y. And then plus whatever is happening with our g of y. Since we integrated with respect to x, we don't know what's happening with y yet, so we just tack on a g of y. So moving forward from there, then we do our partial. So partial of f with respect to y, we differentiate what we were able to make so far in function f, treating now y as our variable. So e to the x is just a constant at the moment. Derivative of sine y is cosine y. X is treated as a constant at the moment. Derivative of tangent is secant squared plus whatever g prime of y is. And again, since they're both partial of f with respect to y, we can set these equal to one another. So e to the x cosine y plus x secant squared of y plus g prime of y is e to the x cosine y plus x secant squared y. Okay, e to the x cosine y drops out, x secant squared y drops out, so we get g prime of y is 0, so then g of y is just some constant. So our f of x, y is e to the x sine of y plus x tangent of y equals c. So we don't need to put plus c1 equals c2. Again, we can just take care of the c's at the end. I mentioned that we're going to have a particular solution to this, though. Right now we just have an implicit solution. If they want a particular solution, then they're also going to give us some initial conditions. So for this one, they'll give us, what did I pick out? Y of 1 is worth pi over 4. So notice I don't even really have this thing solved for y. I don't need it to be solved for y. I know that this guy I'm going to plug in where the y's used to be. This guy I'm going to plug in where the x's used to be. And that will allow us to find c. So then we have e to the 1 sine of pi over 4 plus 1 times tangent of pi over 4. Pi over 4, remember that guy is 45-degree angle. So your sine is root 2 over 2. So now we have e root 2 over 2. E of the first is just e. We have 1 times sine and cosine are the same, their ratio is a 1. So then our c value is e root 2 over 2 plus 1. So then our solution, I am out of real estate vertically, so I'll just a little barrier here. So our f of x, y is equal to e to the x sine of y plus x tangent of y is equal to, instead of c, now we know what c is given these initial conditions, so e root 2 over 2 plus 1. So that is as far as we will take that one. That is our sort of original equation that we differentiated both sides to get what they started us with, this differential equation. So that's our particular solution. So in our next at-bat, we find out, okay, well, what happens if when we do our check to see if it's an exact equation and it doesn't turn out exact? For that, we need what's called an integrating factor. The formula for how you find the integrating factor, you don't need to memorize that. You do need to know how to put that formula to work. All right, so first let's see a problem. So we'll do sine of y by x plus 2 all over x times dx plus cosine y dy is equal to 0. So we're in the right format. We have something times dx plus something times dy, and we're equal to 0. If you're not in that format, get to that format. So then we do our check to see if it's exact. So m, remember, is a derivative with respect to x, so we'll switch it over to y. So that means this x plus 2 all over x is treated like it's a constant. Derivative of sine y is cosine y. Partial of n with respect to x. So n itself was a derivative with respect to y. Now we'll differentiate with respect to x, and we hope these guys match. But the derivative of cosine y when we're treating x as if it's the only variable in town, cosine y gets treated like it were as if it were a constant. That's worth 0 then. So these two are definitely not equal to each other. That's a situation where we then need to go to an integrating factor. So we choose one of two factors. Either mu of x is e to the integral of partial of m with respect to y minus partial of n with respect to x over n, integrate with respect to x, or mu of y is equal to, basically switch them around, e to the integral of n of x minus m of y over m, and do that one with respect to y. Just as a heads up, if either of these churns out two variables left when you're done integrating that, use the other one then. I'll use IF for integrating factor. So if there exists two variables in your e to whatever power that you found, use the other integrating factor. So if you found it with x and you got two variables in it, try finding the y instead and see if that knocks it down to 1. So for this one, I'm going to calculate both, and one of them would be sort of easier to work with than the other. So mu of x It's e to the integral of, so partial of m with respect to y, that was our x plus 2 over x times cosine y, then minus partial of n with respect to x, that was 0, over our original n, so over cosine y. So then this is e to the integral of the cosine y's drops, and so the minus 0 just is gone. E to the integral of, and we can split this up. We can call this x over x is 1, and then 2 over x, or 2x to the negative first, whichever you prefer, and we're integrating this with respect to x. So we can either use mu of x, try to make sure you can tell this is a mu, not an m. Mu of x is equal to e to the x plus 2 natural log x, which is e to the x, e to the natural log of x squared. So e to the natural log of x is, of course, x, or just x e to the x. So one option is to take each term of the original and multiply it by x e to the x. Our other option is to find mu of y. So same idea, we just flip the order and integrate with respect to y instead of x. So e to the integral of partial of n with respect to x, 0, minus partial of m with respect to y, this lovely x plus 2 over x, times cosine y, and all of that is over m, which our m was sine of y by x plus 2 all over x. My apologies, this should be over x as well. We're integrating that with respect to y. Obviously, there's some cleanup that can be done there. So this is e to the, those will drop, opposite of cosine y over sine y times dy, and we're integrating. So mu of y is then the e to the natural log of sine x, and that is negative as well. So if you differentiate natural log of sine x, u prime over u, my apologies, that is a y, u prime over u, derivative of sine is cosine, keep sine at the bottom, so we do have that one extra negative there. So we can turn this, we can do a little bit more manipulating on this. The negative can be turned into a power. So this is e to the natural log sine y times e to the negative 1. So we're raising to the negative first power. So power to a power, our shortcut is we multiply. That's how the negative 1 is out there. And then e to the natural log of sine y will just spit out a sine y. So this is 1 over sine y, cosecant y if you like it that way. So this one would give us a little bit more cancellation, a little bit simpler to work with. So I'm going to go ahead and use the 1 over sine y. So I'm going to multiply each of these three terms by 1 over sine y. So 1 over sine y times sine y by x plus 2 all over x times dx plus 1 over sine y times cosine y times dy is worth 1 over sine y by 0. Of course, it's going to give us a 0. So the sine y's drop. So we either have x plus 2 all over x, or if you like, you can split the fraction, call it 1 plus 2 over x dx plus cosine over sine is cotangent, so plus cotangent y dy is equal to 0. All right, so now we basically treat this as if it's a new problem. We find our check. In fact, let me just transfer this to the next page so I don't run out of real estate here. So we have 1 plus 2 over x times dx plus cotangent of y times dy is equal to 0. So partial of m, treating y as if it were the variable, is 0. We don't have any y's here to work with. Partial of n with respect to variable x, same deal, equal to 0. So now they are equal to each other. Therefore, there exists some function xy such that partial of f, treating x as the variable, gives us this new version of m of x. So 1 plus 2 over x. And partial of f with respect to y gives us the cotangent of y. So we'll integrate. Giving us f of xy. Antiderivative of 1 is x. Antiderivative of 2 over x is 2 natural log x. And then we'll add on g of y. Whatever function is happening with respect to y is involved as well. So partial of f with respect to y. So now that we found what the general format of f looks like but don't know much about y, differentiate it with respect to y. First two terms are gone, so then that's g prime of y only, and then that is equal to cotangent of y. So we integrate both sides of that. So g of y, integral of cotangent is natural log of sine. So remember, u prime over u, derivative of sine is cosine, and keep the sign at the bottom. Cosine over sine is cotangent. So now we can say that our function with respect to x and y will be x plus 2 natural log of x plus g of y, so plus natural log sine of y. It's worth some constant. Occasionally you'll also see these guys put together, so you may also see it. I'd be fine with it left this way. You may see it sometimes written as x plus natural log of x squared sine of y is equal to c. So the 2 coefficient becomes an exponent, and adding with the same base becomes the log of the product. Again, either one of those is just fine with me. I'm perfectly fine if you stop here. If they want any more detail on that, if they want us to find c, they have to tell us something about x and y. They would have to give us some initial conditions. Okay, so some problems to try out from 2-4. I would try 1 to 37 on the odds. If you have any questions, please get in touch. Otherwise, I will see you next time.